Hi, so today I'm going to be making an infrared sensor, more specifically indium antimonide, and what I'm going to do is deposit a thin layer of indium antimonide, and I'm going to deposit it on a silicon substrate and then show you how it senses infrared light. So I'm going to first walk you through the machine that I'm going to use to deposit this, called a Physical Vapor Deposition machine, and then we're going to deposit the indium antimonide, and then we're going to measure its photoconductive current to show that it indeed is a sensor. So I'll refer you to my previous video on photoconductive current measurement if you're curious about that. But without further ado, let's get started. So this is the plasma vapor deposition machine that I'm using. It's a Kurt Lesker PVD75 Proline, and as you can see, these are the pressure gauges of the chamber and the load block. And what I'm gonna do is I'm actually gonna bet the chamber to load in my source materials. So there's like quick actions that I can just take here. Makes it very simple. So process chamber vent, and once this is done, I'm gonna load in my materials. These are the samples that I'm using, so I put them in the desiccator to avoid any moisture. And so you have silicon, so this is just straight up silicon, very lightly doped silicon. The other one is antimony, which is what we're gonna be using today. And we also have the zinc pellets, which is also something that we're gonna be using today. And these are indium and gallium. That's also gallium. Okay, so the chamber is finished venting, and now we can look into the chamber. So just to quickly walk you through it, this chamber has, I have to ground it before I can touch anything. This chamber has E-beam evaporation and thermal evaporation. And what E-beam evaporation does is it hits the material with a beam of electrons, just like the name indicates, and you're essentially depositing, when it heats up, it vaporizes, and you're depositing the vapor. Onto your substrate. And this is the E-beam section. So that's the source material for E-beam evaporation, and similarly that's for thermal. And for thermal, you just heat up the material until it starts evaporating. Okay, so I added my zinc source in carbon billet, or a carbon crucible, and that I'm gonna use that for E-beam. So oops. There we go. So there's already some, I'm not sure if you can see it, but there's already some zinc in there. I just added a couple more pellets. Now it's time to load the antimony. And for antimony, we're gonna load it on there. So we already had antimony on there before, so I'm not gonna, as you can see, I'm not gonna replace the boat. I'm just gonna place more on there. Okay, so I loaded up the antimony, as you can see right there. I couldn't film it as I was doing it because it requires two hands, but now I'm just gonna close that, and that should be it. And just so you know, the E-beam is not for the E-beam, this is not the only material that we have. If I can get this right. Yeah, we have several materials, as you can see. So that, for instance, is titanium, that one is silicon, and that one is gallium. So I'm just gonna go back to zinc. And the idea is to only have 2/3 full. So in fact, I kind of have a little too much, so I'm going to take out some and then close the chamber. Before I close the chamber, I also wanted to show you that these are the sensors, like the crystals that sense the thickness. So we have 1, 2, 3, and 4 sensors. That's for E-beam and 4 for thermal. And over time, you have to replace these crystals. So actually, 2 of these are kind of need replacement, so I'm going to do that right now. So this is the first crystal, and it's fairly easy to top it off. And these are some of the replacement ones. So the gold stuff that you see is gold, and we want that to be facing outward. So I'm gonna put one of these on here. It's hard to do it with one hand, so I'm gonna pause and then do it. Show you when I finish. Okay, so I actually replaced both. You can see how worn down the other one was. And again, it's fairly simple to just pop this in. And yeah, we should be all good to close the chamber. And that is indium, the other thermal source. So just double check everything is okay and can close it. Okay, the chamber is closed. You can see the two crystal qualities that I replaced are 98 and 96%. The other one, for instance, that I didn't replace is 70%. And I'm just going to go back to the deposition and then pump the process chamber. This is going to take a while, and I'll show you when I'm done. Okay, so now I'm preparing the substrates. I'm going to be using two. The first one is N-doped silicon, and the other one is fused silica. By the way, there's another deposition tool, an older one here. Pretty cool. So I'm gonna be taking out one of these quartz wafers. It's hard to do with one hand, but yeah. And I'll cleave the silicon, which I'll do in a second. Okay, so this is just a section of the silicon that's been cleaved off, and I think I might cleave it down the middle.
Okay, now I vented the load lock, and I'm gonna be placing the wafer in there, our new wafer sample in there, so to carefully take this out. And you see older wafers that I had? I'm gonna be getting rid of these and replacing it with our new, not fused silica, but I'm gonna be first placing the silicon and then later on fused silica. So this requires two hands, so I'm gonna stop there.
So I placed it inside the load lock, as you can see. And one of the interesting things with this is you should wipe these like rubber seals with just the chem wipe and with isopropanol. Otherwise, you're gonna have like some dust particles that actually prevent it from pumping down to the right pressure. So, which in our case is like the transfer pressure is around 1E-6. So, yeah, I've noticed this, like it gets stuck like at 1E-5 or something, and it can't pump down. So, yeah, I'll do that right now. So it's just chem wipe with some isopropanol, and I'm just lightly wiping this off. And this also goes with the chamber seal as well, with the main chamber, process chamber seal as well. So now I'm ready to pump the load block. It's gonna take a few minutes, and then we'll load the substrate onto in the process chamber. Okay, so just to go over the recipe that I'm going to be using, I'll show you how I made it. So these are a bunch of sub-recipes within the recipe. And for instance, I'm just going to, let me start with this. So for instance, I heat up the sample to a temperature that I want. So I'll go into that sub-recipe, and you're going to have a bunch of specifications. So for instance here, I'm heating it up to 100 degrees C. And each of these is, again, a sub-recipe within it. So the interesting one is going to be the deposition of seed layer of titanium, and that's because the wafer is silicon, and sorry for the noises, but that's because the wafer is silicon, so we're going to need a seed titanium layer. Then we're going to deposit zinc, and then we're going to deposit antimony. So for zinc deposition, again, it's going to have its own sub-recipes, and actually for this case, it's going to have sub-recipes of sub-recipes and so on. And it does different things, like deciding the material deposition rate and the material deposition thickness. So interestingly, what I'm doing right now is actually, instead of depositing a layer of zinc and then antimony and then calling it good, I'm depositing zinc, a little amount of zinc, I think 30, what we calculated, which is 30 nanometers, I believe, and then 45 nanometers of antimony. And then I'm going to do that repeatedly until a total thickness of 180, and this is in kiloangstroms. So until 180 nanometers of zinc thickness is achieved. So yeah, it's just basically a little for loop that checks thickness and then goes back. And the reason is it's better to, I'm trying to get them to react, right? So it's better to have like thinner layers of each, and then have like one blob of zinc and one blob of antimony to do that. So this is what it looks like at the end. You can see those lines right here and here are where are where I was holding the wafer. Okay, so there you have a better look. Now I'm going to be doing a conductivity measurement on this, photoconductance measurement, and also EDS, which is going to tell me what the actual. Okay guys, so this is what the final product looks like. I'm actually coming back to you after a few months, and I actually made indium antimonide instead, so because that's a well-known material. But what you see here is the film deposited on silicon, and you can see where the holder on the PVD machine was. Like you can see that little change in the surface. But yeah, the gray area, or the more shiny area is the film, and it's I placed 2 probes on it, and the things that you see right here, they're indium pads. So indium helps make better or more ohmic contact than just doing simply copper. And essentially what the setup does is we're going to be shining light from an LED at a certain frequency. So in this case, we're shining light of 780 nanometers, and that's sufficiently larger than the band gap of indium antimonide, which I believe is around 0.8 something. So it's sufficiently larger, and 780 is around, I guess it's around 1.5, 1.6. So it's sufficiently larger, so we can excite the electrons from conduction to valence band and then get our signal. So essentially we're using the mechanism that we talked about in the other video, which is photoconductive current. So we're modulating the light at a certain frequency and then amplifying that to get the actual current, photoconductive current. And you can see we're going to be measuring that there. So for instance, in this case, you see around, don't worry about the actual like value of the just look at the magnitude. So it's around 0.35, and you see the laser, the LED is on. So the little LED is on the bottom of this. So it's on, but it's not directly above the wafer. So what I'm going to do now is I'm going to place it right above the wafer. Not sure if you can see that. Sorry about that. But I'm going to place it right above the wafer, and I'm going to try and position it in the middle. So you can actually see. So right there, you can see it on the indium. But I'm going to try and place it on the actual film, and I think that's good. So the idea is when I'm placing it directly on there, then the signal should increase. So you can see the signal that's picked up, that magnitude is much larger. Now, indium antimonide, these films don't really perform as well as like bulk materials. So there is an increase, but not that, like, not a mind-boggling increase. I'll put another video here of one of the crystals that I work with, the new material that we're working with, barium cadmium phosphide, and you see like 6 orders of magnitude increase when you're shining the light. So yeah, and okay, so this is how we actually properly quantify the photoconductive current. So what we're going to be measuring is from minus 2 volts to 2 volts. So step size of 200, and we're going to 21 steps to 2 volts. And essentially what we want to see is we're measuring the magnitude of the photoconductive current. So what we want to see is a decrease up until 0 bias, and then an increase again. So we want it to make a V, right? So yeah, maybe I can speed this up so you guys can see it measuring real time. All right, so you can see that I'm just gonna put this aside, but you can see that it's not perfectly a V, and that is because we form a little metal semiconductor Schottky. So that's why it's like behaving not perfectly it's not perfectly ohmic, that's why. But the idea remains the same, that what we're getting is due to the carriers generated from, or the photo generated carriers after we made our indium antimonide film on silicon.